Hello everyone, hope you're all doing well, having a great time and staying safe. So this is science lesson class 5, unit 6, chapter 2 and section 3. And in this lesson we will try to talk about work and power. Enjoy! Okay, before we start today's lesson, let's do the section review on page 261. So the first question says, what happens to an object when a balanced force acts on it? Your answer should be, if two equal forces act on an object in opposite direction, the net force will be balanced and object's motion will not change. Or you can say, whenever a balanced force acts on an object, the object will not change its motion. The second question says, a moving object speeds up. Are the forces acting on the object balanced? Explain. Since the moving object is speeding up, this means that acting force on an object is not balanced. The object is speeding up. The two forces on this object are in the same direction. That's why the object is speeding up. The third question says, suppose you ride a bike along a flat, straight road at a constant speed. Are the forces acting on the bike balanced or unbalanced? Since you are moving, this means that it is unbalanced force acting on a bike. The fourth question is the critical thinking. Two bumper cars collide. Both cars stop. How do you know that the forces has act on both cars? Well, to answer this question, you need to know the basic law of science, which is that all the forces act in pairs. When one object acts on a second object, the second object also acts on the first object. So we know that a force has act on both cars. The last question says, suppose a book weighed 35 Newton and you applied a force of 50 newtons to lift it. So you are lifting the book. The net force acting on a book is 35 newtons up, 15 newtons up, 15 newtons up, and the last option is D, which is 35 newtons down. You know that the book weighs 35 newtons and you have applied 50 newtons to lift it, so it is up. 35 plus 50 is 85 newtons up. So your answer should be A. Let me start this lesson with a question. Have you done your homework? And some of you didn't do it, others did it. Now, if I ask those who have done it, did you do a lot of work? They would say, yes, it was very exhausting, tiring process. But have they done any work? Well, scientifically, no, they didn't. Because a work, according to the scientist, is something very different with the kind of work you are familiar with. So to understand how the scientists define work, imagine with me, a gardener is trying to pull an old tree stump out of the ground. He pulls and he's trying his best until his face is red and he is all sweaty, but the stump does not move. So, did he do any work? This would be our first question. The second question is, what about a little boy? This little boy is with the gardener, riding his tricycle from one end of the garden to the other, circling around the gardener along the way. After several rounds, he stops at distance about 15 meters from the gardener, who is trying to pull the stump of the tree. Now, which one of them did work? Who did more effort? To answer or to be able to answer this question, you need to learn what is work and what is effort. Let's go back to our story. Clearly, the gardener used a lot of effort than the boy because he's applying much larger force. But according to the way scientists define work, he has done no work. What a shocking, yes. Because work is the use of force to move an object through a distance. So since the stump of tree didn't move, no matter how much force he applied, the gardener didn't do any kind of work. On the other hand, the boy was actually moving himself and the tricycle along the sidewalk, right? So according to the definition, the boy has done work. So one more time, what is work? A work is the use of force to move an object through a distance. The use of a force to move an object through a distance. A work is the use of force to move an object through a distance. Don't forget this. Let's calculate work. How should we find a work? And what is a unit of work? Well, the metric unit of work is joule. Joule is the metric unit of work. So a joule is the metric unit of work. How should we calculate work? Let's say we want to know how much work the boy done. Well, in order to know the exact amount of work done by the boy, you need to multiply the force used to move an object or the object by the distance the objects move. So to know the work or to calculate the work, you need to know the force and the distance. Multiply the force by the distance and you find out what is the work. So I think this part is very clear, since you're seeing the equation that you can find a work with it. So the equation says work, the unit of work is joule, force is Newton, and distance is meter usually. So usually this equation is used to know what is the amount of work done by any object. There's an example in your book in page 265. It says the average fifth grader does about 200 joules of work getting out of bed in morning. When a 1,000 Newton basketball star jump 1 meter to slam dunk the ball, he does about 1,000 joules of work. Obviously, since he is doing 1,000 Newton of force, and we multiply the force by the distance that a basketball player goes through, which is 1 meter. So the amount of work the basketball player did is 1,000 joule. A meter multiplied by Newton is joule. Let's talk about the example that you are seeing right now in front of you. The example says if a weightlifter lifted the barbell calculate the work done if the barbell weighs 1,600 newtons and he lifts the barbell 2 meters. So this is your homework. I'm pretty sure it's very, very easy and you can find it. Let's talk about power. What is the power? Power is the amount of work done for each unit of time. So power is the amount of work done for each unit of time. Okay, let's say the average adult could probably push a small car along a flat road, right? The car's engine could also move the car along the road. Even though the person and the engine do the same amount of work, the engine can do the work much more quickly, right? So the engine can do work much more quickly. The engine has more power if you compare it to a person. The metric unit of power is watt. W-A-T-T is watt. 1 watt equal doing 1 joule of work in 1 second. For example, lifting an apple 1 meter requires about 1 joule of work. To lift that apple 1 meter in 1 second takes about 1 watt of power. The equation that you're seeing right now in front of you is the equation that is used to find the power. Let me give you another example. A person who weighs about 400 Newton does about 1,200 joules of work. Climbing 3-meter flight of stairs. So what is the work? In this case, finding the work is very easy. You just have to multiply the amount of force to the distance that the person climbed, which is 3 meters. So multiplying 400 Newton by 3 meters is 1,200 joules. So how can we find the power from here? It is basically dividing the work, which is 1,200 joules, by the amount of time it takes for that person to do that amount of work, which is basically 3 seconds. So if I divided the 1,200 joules by 3 seconds, I will get the power, which is 400 watt. You can find this example in page 265 if you want to look at it. Talking about simple machine and work. You know that whenever we want to lift a heavy object, it takes a lot of work to do it. But what makes it easier, or what makes our work easier, is using simple machine. Simple machine is something that makes our task much more easier. How? By changing the size or direction of the force, or the distance over which the force acts. So simple machines change the size or direction of the force, or the distance over which the force acts. But you will have to know that simple machines do not change the amount of work to be done, but make tasks easier by exerting a smaller force over a longer distance, or changing the direction of a force without increasing or decreasing it. The example that you are looking at right now is an example of a pulley. A pulley consists of a metal wheel with a rope or chain passing over the wheel. When one end of a rope pulls down, the wheel turns and the other end of the rope moves up. The fixed pulley changes only the direction of the force, the effort force. But It does not change neither the size of the effort force nor the distance. But in the case of a movable pulley, when you pull one end of the rope, the movable pulley rises with the object it is lifting. Movable pulley does not change the direction of the effort force but decreases the size. We mean that it decreases the size of the effort force. So to lift a 1,000 Newton piano by a fixed pulley, you need 1,000 Newton force to raise it 1 meter. While if you use a movable pulley to lift it, you must exert 500 Newton force to raise it 1 meter. You can see the example of a fixed pulley in the next slide also. We reached the end of this lesson, so your homework will be the chapter review in page 268, 269, and good luck!